We've considered substances in isolation and the properties that arise from their intermolecular forces. We would also like to consider what happens when we combine them together, and it turns out that their intermolecular forces remain very crucial in determining their overall properties. If we are unable to identify the substances independently that we have mixed together, so we can't view particles of them, we can't even separate them using something simple like filtering, then we have what's called a homogeneous mixture or a solution. This is when the substances combine together and there's no differences in the phase, it just becomes a single phase. Now, we often refer to the solvent, which is the substance in which the other substance is dissolved. And if one of the substances is minor in comparison to the other, so there's a smaller amount of it, then we often call that the solute of the solution. Examples of solutions include antifreeze. This is a solution made by mixing two liquids together, ethylene glycol and water. We could also mix a gas with a liquid, soda being an example, where you have CO2 mixed with water. Seawater, you have a solid, which is salt, mixed with a liquid, which is water. We can have other solvents than water. Water just happens to be a very good one. It's good at dissolving other substances. Brass is a solution of zinc and copper, or you could think of it as copper and zinc. Both act as solvents for the other. Air, we have various gases mixed together, all acting as solvents for each other. And again, when we talk about solute, we usually are picking on a minor component, but we're always welcome to have multiple solvents. And because CO2 is the least quantity here, we might say that it's the solute, but we can just as well call it a solvent in which these other substances are dissolved. Contrariwise, if we have something like fog, this contains a gas, which is the air. It contains a liquid, which is the water. But these are not well mixed. The water remains independent of the air, and so that is not a solution. It's not all of one phase. Jello seems kind of solid. That's because there's a protein complex which is formed. But that protein complex is trapping the water which was present, and they do not combine together into a single phase. They remain distinct, which means that it's not a solution. Sand is a mixture of different kinds of rock, such as quartz and igneous rock. You could have various kinds of sedimentary rock. It's a pretty broad genre. Salad dressing, you take oil and you mix it with vinegar, but the oil and the vinegar remain separate. There's little beads of oil floating around inside of the vinegar. And so those are all instances where, despite having multiple substances, we don't have a solution. The molecules are not well mixed. Why is that? Why do we sometimes mix liquids together and we get solutions, and sometimes we mix liquids together and we don't get solutions? There are two factors which determine what's going to happen. The first factor is entropy. Entropy you can think of colloquially as the disorder of the system, and our systems would like to increase their disorder. And this happens when we mix substances together. It becomes more disarrayed. So that is always favorable. Now, if it's always favorable, why do we not always form solutions? Because there's another factor, which is the energy of our system. Systems tend toward their lowest energy state, and what that's going to be and whether or not we reach it through mixing is going to depend on the intermolecular forces involved. What do we mean when we talk about entropy as disorder? Technically, what we're really talking about is the number of possible arrangements of the system. A system which has more possible arrangements is more disordered. A system which has less possible arrangements is less disordered. We categorize these by talking about the macrostate of the system, which is the overall look of the system, and the microstate of the system, which is the various configurations which correspond to that overall look. Now, for example, you might have a messy room or you might have a clean room. So those would be two macrostates of the system. The clean room has maybe just one microstate associated with it. You can have all your laundry neat and folded in your drawers and your Star Wars collection all organized in your top shelf. But if we consider the messy configuration, then there are lots of different ways that that could present itself. Your underwear could just as well be hanging from the lamp as dangling on the floor or off the side of a dresser. Now, your mom comes in. She's not going to distinguish between those various microstates. To her, it's going to look the same no matter where your underwear is draped from. And so that's kind of why your room gets messy, is because there are so many more configurations for where things can be and have it be messy rather than have it be clean. So you have to go through a special effort in order to ensure that it's in the clean configuration. That is, in essence, what we're talking about with entropy. Well, same thing happens when we're dealing with solutions. So if we have a nice crystal, let's say this is a sugar crystal, sugar doesn't really have a significant energy difference, whether it's existing as a crystal or if it's dissolved in with the water molecules. So if there's no energy difference, then why does sugar dissolve? Well, the reason is because of entropy. So there's one possible configuration, we might think, where we have all the crystal molecules organized, versus if we instead have a solution, then our molecules are dispersed in random configurations. Now, these molecules are randomly moving about. Every time a water molecule collides with a sugar molecule, they might have the opportunity to swap positions. Now, they could just as well swap back afterwards, and we would maintain our crystal macrostate. But what's more likely, that we're going to have another swap that it undoes this, or that a swap is going to occur with one of the surrounding molecules and carry that molecule further into the solution. So there's not really any rule which says these molecules all have to disperse. They could stay in the corner of the container if they liked. But this random process tends to result in them being dispersed. And we don't really distinguish between the various cases where they're dispersed. There are so many of those cases that when we actually look at this system at some time afterwards, that we're almost certainly going to observe one of these situations rather than our ordered situations, even if both are possible. So this first case is our low entropy case, where we have only one microstate corresponding to the crystal macrostate. And our second case is the one with many microstates, and that's the one that we are going to tend to over the course of time. That's why substances tend to dissolve, given the opportunity. However, while we've explained why something like sugar might dissolve in an aqueous solution, if we were to add something like magnesium sulfide, it would not dissolve noticeably. So clearly not everything dissolves, even though that's entropically favorable. And the reason for that is because we also have to consider whether it's energetically unfavorable. In order to predict whether or not we're going to have to deal with energetic unfavorabilities, the first thing that we need to do is we need to determine the intermolecular forces present in the solvent interacting with itself and the solute interacting with itself. Now we're going to consider the case where we form a solution. And so these will be the intermolecular forces between the solute molecules being dissolved amongst the solvent molecules. Now, if those interactions are comparable to the interactions where the substances are unmixed, or if those interactions are stronger, then we probably expect that we're going to form that solution. Let's consider some substances and see if we can have some insight into whether or not we're going to form a solution when we try to mix them. So we have ethanol and ammonia. We have carbon dioxide and ammonia. We also have oxygen and fat. So we need to consider those intermolecular forces. So we're going to need to have a picture of our molecule here. Now, ethanol, we have these bond dipoles between the carbon and the oxygen. the oxygen and the hydrogen. So if we consider the net effect there, we expect to have a net dipole resulting from those bond dipoles as so. Ammonia also has bond dipoles between the nitrogen and these hydrogens. And the overall effect is that there's going to be a dipole pointing downward. With carbon dioxide, we also have bond dipoles between the carbon and the oxygen. But those cancel out. So there's no net dipole there. Oxygen with oxygen certainly doesn't give us any bond dipoles. So that's nonpolar. And fat might be difficult to draw, but it's a hydrocarbon. So it has chains of carbons with lots of hydrogens attached to them. And there's not a significant difference in electronegativity between the carbon and the hydrogen, so probably no dipoles in our fat either. All right, well, when our ethanol molecules interact, we have these dipoles here. We have hydrogen attached to an electronegative element, and this hydrogen can interact with this dipole if we make a copy of this molecule and associate with those lone pairs there. Now we have the criteria for forming hydrogen bonds. Hydrogen, as part of the dipole, can interact with a very electronegative element that has lone pair electrons on it. So we can certainly have some hydrogen bonds. Now, what about when we have ammonia interacting? It also has this lone pair of electrons on an electronegative element. Hydrogen is part of a dipole here, attached to a very electronegative element. So when we copy this ammonia molecule and set another one next to it, one of these hydrogens could associate with the pair of electrons on that nitrogen in the other molecule, and we would have a hydrogen bond. So in both of these cases, we have hydrogen bonds. When they interact with each other, we could certainly have this hydrogen interacting with that lone pair and those nitrogens, or these hydrogens interacting with those lone pairs and that oxygen. So again, we have some hydrogen bonds. Well, because in all cases we have hydrogen bonding, then we expect that this is going to be soluble. There's not a high energy cost associated with mixing, and since mixing is always entropically favorable, then probably we're going to be able to form the solution. All right, well, what about when we have carbon dioxide and ammonia? So we already know that ammonia by itself has hydrogen bonding. So it's the solvent again. Now the carbon dioxide, it's nonpolar. And it's not ionic. So the best that we can get out of that is that we have London dispersion forces. Now when we have the CO2 interact with the ammonia, well, we need to have at least two dipoles in order to have dipole-dipole interactions. We only have one dipole in the ammonia, so when it comes in with this nonpolar molecule, there's not going to be any dipole action going on there. So the best that we're going to be able to come up with is London dispersion forces again. All right, so in order to form this solution, we're going to have to give up these wonderful hydrogen bonds enjoyed by ammonia interacting with itself. We're going to have to break them and stick these CO2s in between, and all we get in return is those fairly weak London dispersion forces. So is that going to happen? No, no way that's going to happen. We're not going to form a solution between these two. And let's consider our last case now. We have oxygen and fat. So oxygen is nonpolar, doesn't have any charges on it. So nothing ionic, nothing dipole going on. That means that we have London dispersion forces. Same thing with our fat here. No dipoles, no charges, London dispersion forces, the best we can come up with. And what about when they interact with each other? Well, we're still going to have London dispersion forces. So there's not going to be any major cost associated with having these two mixed together instead of remaining as components. That means that we probably will be able to form a solution here. Now this is a good thing that oxygen is soluble in fat and nonpolar things. That makes it very easy for it to traverse something like the lipid membranes in your cells. Some cold water fish, because oxygen solubility goes down in cold water, they even have conduits of fat throughout their body as an easier way of transporting oxygen around in those very cold conditions. And that's a great way to figure out qualitatively whether or not we expect we're going to create a chemical solution. But we might also want to know what the exact energy is going to be, whether it's a benefit or a cost when we do form these solutions. And the way that we measure this is by using an enthalpy of solvation. So this is the energy given off when we take 1 mole of our solute and dissolve it into our solvent. Now there's a problem here, which says this would be very difficult to calculate. We don't know how many solvent molecules are interacting with our solute, and there's lots of bonds forming and breaking going on. So how are we going to arrive at this solvation energy? Well, our solution is a trick we've used before. We have Hess's law, which says that if we can just imagine the process as happening in steps, it doesn't have to actually happen in those steps, but if we can imagine a series of steps that would lead to the observed state of our system, then we can calculate the total energy of our system just by adding together all the different energy changes for all those different steps. Let's look at a solvation reaction where we have magnesium sulfate, and we put this in water, and so it becomes aqueously dissolved in the water. Well, so we'll actually have magnesium 2+ ions and SO4 2- ions in our solution. This is an exothermic reaction, so this is how hot packs operate, at least some of them. This gives off a lot of energy, so all you need is to just have a barrier between your salt and your water, and you break the barrier, they mix together, and then the heat is given off and go into your hand. Now to break this into steps, let's start with our hot pack, maybe all divided up. So we have the liquid part and we have the solid part. Now let's imagine that we are able to separate those solute molecules. So we'll do that in a single step, and we'll perform another step, and we will separate the solvent molecules. And we have to do these to make room for each other. So now we have gone up this quantity of energy to pull all of our ions apart. Recall that that's what's called the lattice energy, the energy required to dissociate your salts and everything into ions. Now, let's go ahead and combine them back together in a solution. That's energetically favorable because now we get to reform all those intermolecular associations that we've broken. So because we're going down on the graph, that's going to have a negative sign. When we're going up on the graph, we're increasing in our energy state. That's going to have a positive sign. Now if we compare the difference between where we started at and where we wound up, we're a little bit lower. So our energy change overall, which is our delta H of solvation, points down a little bit, which means it's negative. So it's exothermic. We gave off this quantity of energy to our environment because we were able to reach this lower energy state. So to calculate this delta H solvation, all we have to do is we just have to take our delta H lattice, or we can also think of it as the components for breaking apart the solute and then breaking apart the solvent. And we add that to our energy change when we mix them together. And we get our overall change here. Well, what about if we consider the case where instead of winding up at a lower energy level, we wind up at a higher energy level? Is that even physically possible? Well, certainly it is. We could certainly have this situation here, but it's going to cost us something. It's going to cost us this quantity of energy to bump ourselves from our initial energy state up to this energy state. Now, where is that energy going to come from? It's going to come from the surrounding environment. So we're going to suck some energy in. Are we allowed to suck energy in? Well, we actually are, because entropy would really like to have this mixed state instead of having these unmixed states. And entropy is a potent enough force that as long as this energy change is only small, entropy is going to go ahead and drive this forward even though it's not energetically favorable. So in this case, we're going to have an endothermic reaction. Now, if this was ammonium nitrate dissolving in water, then this would be what gives us you a cold pack. And so it sucks in that energy from your hand when you use it and provides that cooling sensation. And so these are not quite as frequent of reactions, these endothermic reactions, but they certainly are common enough. So our conclusion here is that even our insoluble substances, even things that don't necessarily want to mix together for energetic reasons, will tend to dissolve, in some cases at least a little bit, thanks to this entropic favorability. It can provide just a smidge of that energy difference that we're missing. And in fact, you can even use this solvation process to drive motors or other things. Entropy has some energetic effects which are important. Well, since small quantities can dissolve in almost all cases when we mix substances together, we probably want to be able to specify what that quantity is and be able to make some comparisons. So this is where we define formally solubility as a number. So it's also whether or not something dissolves. We say it's soluble or insoluble. We can also quantify an amount of solubility. So this will be the maximum quantity of the solute that will dissolve in some quantity of the solvent at a specified temperature. So an example of this would be oxygen and water. So oxygen we found was nonpolar, water is polar. So oxygen would not like to be in water if it can be dissolved in something else. But entropy will drive that process forward at least a little bit. And so we get a very small quantity of dissolution of oxygen, 14.6 milligrams per liter of H2O. And this is at 20 degrees Celsius. And supposing we have reached that point where we have the maximum quantity of solute dissolved in our solvent, then we say that that solution is saturated by the solute. And we also define the term unsaturated to mean anywhere below that point where we have less of the solute than would be needed to reach that saturization condition. We also define the term supersaturated to mean that we've actually packed in even more molecules than would normally dissolve. Now, because that's more than is usually possible, this is unstable. An example of that would be the carbon dioxide dissolved in soda water. Because it's supersaturated, then this CO2 is spontaneously leaving the solution. Now, as it continues to leave the solution, eventually it will return back to the more natural saturation point. Well, let's say that we have a liter of water, and we bring this liter of water to a boil, and we are able to dissolve 400 grams of salt in our liter of water. But then we let it cool back down. It cools all the way down to 35 degrees Celsius. We don't observe any salt precipitate out of our solution, so it must all still be dissolved in the water. What kind of solution is it? Is it supersaturated? Is it undersaturated? Is it saturated? Well, what we need to do is we need to look up for these conditions what its saturation point is. So we have this saturation curve here, which tells us the amount which can dissolve for every 100 grams of water at particular temperatures. Now we are at 35 degrees Celsius. So let's look at 35 degrees Celsius here and scroll up to sodium chloride. And sodium chloride, if we were going to estimate this, I think it's about maybe 34 grams of sodium chloride per 100 grams of H2O. So that would be the saturation point. Now we need to figure out, are we above that, are we below that, or are we exactly at 34 grams for every 100 grams of water? Okay, well we have 400 grams of sodium chloride, and a liter of water weighs a kilogram. So we have 1,000 grams of water. And if we make that into amount of salt per 100 grams of water, that will be 40 grams of sodium for every 100 grams of water. Now 40 grams per 100 grams is a larger quantity than what we read off of our chart at 35 degrees Celsius, which was 34 grams per 100 grams. So because it's larger, we must have a supersaturated solution. Now this is an unstable condition, so at some point we are going to lose this 6 grams difference. It's going to precipitate out as solid salt, and then we will have arrived at a saturated solution. We can actually apply this in a very useful method called recrystallization. Now the problem when we perform reactions in the laboratory is that we often introduce contaminants. We often have some unwanted molecules mixed in with the substance that we've produced, and it may be very bad to have that contamination. We want to have a pure sample at our disposal. So how are we going to be able to achieve a pure sample? Well, a handy fact about forming crystals, they tend to push out impurities. They like to line up the molecules without having other molecules in the way. So what we can do is we can take our substance that we've produced from our experiment and we dissolve it in a hot solvent until we have created a saturated solution. So we'll take as much of it as we possibly can and try to dissolve it in our solution. And we can always just add a whole bunch in and then pour off the liquid, and the liquid that we pour off is going to be saturated. So now we are going to cool our solution. So like we did in the previous example, we're going to have a supersaturated condition. And now that extra solute, which is in the solvent, is going to come out of the solvent since it's an unstable condition. And it's going to come out in the form of crystals. Now as these crystals grow, they're going to exclude some of those impurities, and we'll be left with a saturated solution. Now a tip here is you want to try and control your temperatures and your solvent to minimize the nucleation sites, the sites where crystals start growing, and especially you want to minimize them for your impurities. You want to ideally keep your solution at a temperature and a concentration where you don't expect your impurities to want to precipitate at all. But in order to make your actual substance precipitate, you're going to have to provide it with a seed crystal. So that's just a piece of the crystallized form. Or you need a nucleation site where it can start forming crystals on its own. So to have a nucleation site, you might do something like scratch the glass to make little tiny pieces of glass. And then some molecules can start adhering to that little piece of glass. And as soon as they do that, then the other molecules can adhere to them. You can start growing your crystal. And here are some examples of that process. So you can recrystallize sugar, get some nice big crystals. That's how you make rock candy. You could also, if you wanted to at home, it's not too difficult, you could recrystallize some bismuth, and you get these really cool big crystals which have this nice luster to them because of the way that the oxide layer affects the iridescence of the metal.